Now, with that said, my big pleasure to give this talk on a recent project with my colleague Nikita Kozodoy and a couple of industry partners who work for a fintech company associated with micro lending. And generally speaking, this project is about sampling bias. And in the context of credit scoring, we also refer to this problem as reject inference. And the overall goal is to propose new methods for addressing the problems that occur in this setting of sampling bias. I think there are already people posting messages, okay, to this chat. That is distracting. Oh, shouldn't look at that. Right, so actually we are working on this problem for quite some time. And therefore, in theory, there is a lot of content available. Today, I'd like to focus on giving you an idea of the actual problem in the introduction and what we aim at achieving. I'll sketch our propositions. There are two of them, and I'll sketch them at least partly to give you an idea what we're doing, and then rather focus on some empirical results that we got from simulation analysis and working with real-world data. That's pretty much the outline. So let's just start by revisiting decision-making in a banking context or in the credit industry. The picture is to depict standard operations in lending. We have customers and they approach us with credit applications. These applications are screened by some scoring model that estimates risk scores. And based on these scores, these model-based estimates of borrower creditworthiness, the bank will accept or reject the incoming application. So there is a natural partitioning of our data into rejects and accepts, and please acquaint with these terms because I'm going to use them frequently in my talk. When speaking about rejects, accepts, I refer to subpopulations in our data, and the accepts, since we lend them money, we will eventually observe whether they repay their debt or whether they don't repay their debt or don't repay their debt in full. The latter group we refer to bad risks or simply bad, and the former group we refer to as good risk, which I think is standard terminology in consumer lending or in credit scoring. The point that is noteworthy here is that by looking at the whole, credit approval process from this perspective, you may call that a machine learning perspective, it is immediately clear that our training data, the data that we use to build models, build supervised learning models, for example, is biased or gives the biased picture of the overall population of potential borrowers, because we only have access to the labels from the accepted clients and lacking the labels of the rejected clients, their potential outcome, you could say, had we given them credit. Lacking these labels, we can't use them in a vanilla supervised machine learning type of framework because there we need labels. And hence, we have this problem of sampling bias. We kind of sample the accepts by using our scoring models. This is why we consider this an instance of sample selection bias problem. And you could ask, okay, well, is that a problem? And to be honest, the answer to is that a problem is anything but easy. And I'm not trying to sell any specific answer. My preliminary answer would be perhaps it matters. And to get some idea, we start with a simulation. Very easy, we just create data in 2 dimensions, drawing data points, potential borrowers from both groups, good and bad risk from multivariate Gaussian distributions with different parameters. And then we simulate this process that I was showing you earlier, this acceptance loop, as we call it, meaning that we draw samples of customers, we score them with a model, then we accept, hypothetically, a set of the data points that we sampled and reveal their labels. We update our model based on the augmented data set with the new labels revealed of the accepts. And then we continue this process of scoring new applications that we generate, revealing the labels of only those applications that make it past our hurdle, our scorecard that displays some minimum credit worthiness, if you wish, based on our scorecard. And this way we grow our data sample. And doing that for a couple of iterations, we run that for 300 iterations. This means we train or retrain our scorecard 300 times on different training sets, each time with more labeled data from those data points previously accepted available. And you observe that after these 300 iterations, the feature distributions of our two hypothetical features, x1, x2, think of these as bureau score and credit amount or some other features that matter in consumer lending. We do see that the distribution of accepts differs from that of the rejects, and more importantly, it differs from the distributions of the population. That is the nice thing about simulation experiments, right? Everything is under your control, so we do know the true population of our borrowers because we simulate them, and then we can compare how the feature distribution differs, and we see this bias here. The accepts highlighted in green have, for x1, for example, larger feature values on average, same for x2. And then playing a little bit with the data generation mechanism, we posit that the severity of this difference in distribution, which actually is this sampling bias or is due to sampling bias, it will increase if data gets more complex. That's a bit inaccurate. What you see here, for example, is what happens if we draw the data points from both classes, the good risks and the bad risks, not from a single multivariate Gaussian, but from a mixture of Gaussians. So then we have multimodal data for good risk and bad risk, and you do see that now the feature distribution of the accepts is even more different from that of the true populations, which I refer to as holdout here on the slide. That's the blue group, the holdout, the true population. And one other takeaway here is that looking at the distribution, the feature distribution of the rejects, it's more similar to the holdout sample. That is to be expected, but the point I'm trying to make is that using the data of the rejects somehow could help us build better models. And again, vanilla machine learning would not allow us doing so. We can't use the rejects natively because we lack their class labels. We don't know whether there are good risks or bad risks since we haven't lent money. That's the problem. And well, basically, we suggest that this problem has or creates at least two problems. The sampling bias creates at least two problems. It impedes the training or the estimation of scoring models. I use both terms interchangeably, sometimes speaking more to our statistic friend and sometimes more speaking to our machine learning friends. It's the same thing. Building models is harmed by sampling bias, but also since our data, our labeled data is not really representative of the underlying population, we also have a problem when we evaluate models. For example, if we perform some champion-challenger type of comparison, which is quite popular in industry, it's not intuitive how to do that right. Or actually standard practices would use only the data from the accepts, which is biased, and therefore we have a problem also in evaluation. And we propose two approaches to address these problems. One for evaluation, we propose a Bayesian evaluation framework that I will look at in a little more detail. We also propose a new or adjusted learning algorithm, which we call bias-aware self-learning, because that we can abbreviate with BASEL, which is kind of nice in a credit scoring context. And An important principle of the empirical analysis and the paper at large really is that thanks to our partner company, we have access to a precious sample of data, an unbiased sample of data. The company, they were giving credit at random. So we have a random sample of approved credit applications without any scoring. And that sample allows us to represent the population of potential borrowers. And then building models on that sample, we can create something like an oracle model, which represents an unbiased model. And comparing our models to the oracle model then gives us an idea how well our propositions are doing, how effective they are. And the graph that you see here is kind of a little sneak preview. It's based on synthetic data, though. We don't make use of this precious sample here. On the synthetic data, you see that the blue line gives you the area under the curve on a holdout sample. And whenever you see blue or me using the term holdout, note this data refers to the true population of potential borrowers. It's an unbiased sample. And we see that we can get an AUC of, well, 94 point something on that sample from our oracle model. In other words, if we train our scorecard on an unbiased sample of data, that's the performance that we get. The standard approach in banking, however, is to use the data from the accepts to develop scoring models. That's the green line, and you see that there is a gap. There is a gap in the performance of these models. Remember, higher IUC is better. This gap here is basically the sampling bias. Let me abbreviate that with SB. That's the sampling bias. And the techniques that we propose, you see that they recover a little bit of that. Our Basel framework can recover a little bit of that. And I should also say, that's another sneak preview, make sure to look at the scaling of this plot. It's a hard problem to work at. Reject inference, fighting the sampling bias is a hard problem to work at. You won't make major progress. And you see that here. The graph sort of, well, don't let me mislead you. The graph is not meant to mislead you. The improvement gains are tiny, but they exist. And I will make the point that they can be consistent if you do this sampling bias correction right. Okay, let's take a look at our propositions. I want to skip over the literature part with regard to time. We are clearly not the first working on that problem. Many others have done so. Many approaches, interesting approaches, look at that problem from different perspectives. You might know the famous Hackman model, for example. So there are traditional approaches to handle sample selection bias. In machine learning, we have studies looking at covariate shift or domain adaptation. More literature in credit scoring examines techniques to artificially create labels for the rejected clients and to then add those rejected clients with estimated labels to the training data, thereby addressing the sampling bias problems. And other streams in the machine learning literature like semi-supervised learning, which we draw at, also active learning, they could also be considered here. But let's move on to the problem that we note in the evaluation bit. For evaluation, what you see here is a plot of the AUC on the holdout sample on the y-axis and the AUC measured on a sample of accepted clients. That's what is standard practice in industry. We train a couple of candidate scorecards using gradient boosting, playing with their meta parameters, and this is how we create the individual points. And then we can measure their performance on x-axis and on the holdout sample. And you do see that there is rather little evidence of correlation in this graph, and that the best model in terms of the accept AUC is rather different from the one which is actually the best model on the unbiased holdout sample. The evaluation framework that we propose achieves a much better correlation between the performance that you can measure and the AUC of the holdout sample, which is something that in practice you cannot measure. That's important to bear in mind. The performance on the holdout sample, we can measure it because we either use simulated data or have access to this precious data set of granting credit at random that allows us to measure the true performance on an unbiased sample of data. In practice, you couldn't do that. So the Bayesian AUC, as we call it, exhibits a nicer correlation between the true performance of a model, which suggests that assessing models using the Bayesian AUC gives you a more reliable signal whether your models are doing well or not. Well, we need some notation in the reminder, but the notation is fairly standard. So Y is a target variable or label, X is data. And note, please, the superscripts that you see, for example, here, we need to distinguish between accepted clients and rejected clients. So superscript A means accepts and superscript R means rejects. And then, well, the Bayesian AUC is actually quite straightforward. We just propose here a way to measure the performance. I start with the AUC, we can generalize that later. To measure the performance of a scorecard in terms of AUC as the expected performance over the unknown labels of the rejected clients. So we propose to use the data of the rejects, which is normally ignored in scorecard evaluation, and then take the expectation over their label distribution. And one way to estimate that would be by Monte Carlo sampling. The labels of the rejects are either good or bad. So it's binary. You can sample them from a binomial distribution. And that's one way of doing it. As common in Bayesian optimization, to do that, the quality of your result may depend on the prior. And there are quite some options to set the prior here. The prior meaning the prior probability of a data instance from the rejects to be good or bad. Our view is that it makes sense to use the current scoring model or the original scores of the rejected applications, if they are available to the bank, to come up with a prior probability. This proposition needs to be taken with a grain of salt because we basically say that these scores, they suffer from sampling bias. And now we use these scores that suffer from sampling bias as a prior in our Bayesian AUC. That sounds questionable. And well, the argument here would be that we have a trade-off. On the one hand, using a scorecard, a biased scorecard to score the rejected clients and use their estimated labels, that's the disadvantage, or that's problematic. That creates some noise. But on the other hand, we can, first of all, leverage the available information in the data of the rejects, which would be this XR. We have all the data of the rejects from their applications. We know their salary, the credit amount, their bureau score, etc. We know all that. Leveraging that information might be useful, and we do so by estimating the conditional probability of the target given X, given the data. And we also create a larger training sample for our scorecards. And empirically, we show that in this trade-off, using the current scoring model to come up with the prior for the Bayesian evaluation is beneficial. We have extensions for other performance measures. For example, performance measures that are more geared toward profitability. We can generalize this Bayesian evaluation framework to other measures. And we also have a simplified version of this Bayesian AUC for the case where you are ready to assume that all the rejected clients are either good or bad. Now, the Basel framework will skip over. From an academic perspective, you can be very critical with this framework because it's essentially a piece of engineering work. We add multiple components together to come up with a multi-stage modeling framework involving filtering data, generating artificial labels for the reject, training supervised models, iteratively doing everything, and then having some early stopping mechanism. The slides will detail all these steps, and you can read up on them if you are interested. I won't touch on all the details of these algorithms, but we can maybe quickly have a little graphical intuition. This is one more data in 2 dimensions. We have accepts in green and rejects in red, and we have 3 classifiers that we train on only the accepts or the underlying population. This is a simulation again. Or we train the orange classifier using the accepted clients plus our Basel framework. And what you basically see is if you iteratively run this algorithm, the classifiers, they adjust. And after some 300 iterations of running the algorithm, iteratively labeling some of the rejected clients that you have, adding their data to the training sample, retraining a scorecard, and then repeating, that is what you just saw, the classifiers change. And what matters for scoring is the slope of these classifiers. And the yellow one, it is more similar to the one which, to the Oracle model, the blue one, which you cannot train in practice because this model you train on the underlying population. That is meant to give you some intuition. We have a bunch of empirical results available using this precious data set that I was indicating. I'll keep an eye on the time, so Ala, in case you're starting to sweat, no worries. We have data from accepts and rejects, and we also have this unbiased sample. That's this one. It's not too big, I have to say. And thus we make use of bootstrapping and similar mechanisms to squeeze out all the information from that sample. When testing our algorithms, there are 2 experiments. One looks at the ability of the Bayesian evaluation to pick better models. We can take a quick look at the corresponding results. Here you see them for the AUC. The idea is that we consider 2 common setups in scoring. One where you try to tune the parameters of a scoring model, that's the PT setup, parameter tuning. Or another one where you execute feature selection, that's the FF setup. And then we build several candidate scorecards, either modifying meta parameters in the PT setting or considering different feature subsets in the feature selection setting. And we try to find the best scorecard out of the candidate set, out of the choice set. We use our Bayesian evaluation mechanism as one selection strategy. We also use the default strategy, looking only at performance of the accepted clients. We have random picking models at random as a naive benchmark. And then we have some literature-based benchmark by reweighting the data of the accepts such that they are more similar to the rejected clients. And we have the Oracle model, which is the theoretical upper bound, if you wish. And well, the results, if you look at them at large across various evaluation measures, we have the AUC, we have BS, which is the Breyer score, we have the partial AUC that is aware of misclassification costs and their asymmetry in credit risk, and we have the bad rate among accepts. We get some consistent results in favor of the Bayesian evaluation. We also see that the advantage is very tiny. And now this brings me to the last bit of results. Of course, there are more results for the framework. I just want to show there are, but I want to look at something more interesting. Does it really add to the bottom line? That's an important question. We're trying to shed some light on this question. Can an organization, a lender, raise its profit by using reject inference based on our suggestions. To that end, we need to simulate profit, and we calculate the average profit per loan. We link that profit to our scoring models using one performance measure, the average bad rate among accepts. And then we need to simulate some key parameters of a loan which drive profitability. What you see here is the last set of results. Depending on different settings for the loss given default, which is one such loan parameter, you note that the Basel framework in yellow compared to the strongest competitor from our evaluation, it's cluster-based reweighting, but don't worry. We do see an improvement. We do see a consistent improvement. Both correction strategies, both bias-aware, self-learning, and cluster-based reweighting improve over the baseline of just ignoring rejects, which most lenders do. They both improve. Basel is better, clearly. But again, watch the y-axis. This is the incremental return per dollar issued. And depending on the loss given default, we again see that these incremental returns can be quite tiny, but remember, it's per dollar issued. It's a meaningful metric. And from here, my view would be that lenders need to decide whether this kind of improvement is promising enough for them to further look into these measures, into these reject inference techniques. And with that, we arrive at the conclusions, but I'll just stop here because I said all I wanted to say. But thank you very much. And maybe we have time for one question or so if Alan is kind with me. And I'm also happy to be available for other questions afterwards. Thanks a lot. Just imagine some relief faces.
Yeah, thank you very much for this nice talk, Professor Lessmann. Yes, we have time for 1-2 questions from the audience. If someone wants, please open your microphone. No? So I don't.
Yes, I have. I can ask one at least. Very simple one. Are we talking consumer credits here, or are we talking house loan? Right? Okay. Okay, that is.
The data came from micro lending, so this is very tiny loans. The framework is generic. I cannot, draw conclusions how effective it is on other data. We simulate microloans and we simulate installment loans. And by simulate, I mean we consider a representative set of loan amounts and interest rates and acceptance rates.
Very interesting. So maybe one more, if you go one slide back, you are inside the 2 sigma bands with all those, if I see it correctly.
Oh, for sure.
Yeah. So
you're referring to the magnitude of performance improvement.
That's right. The marginal improvement. Yeah, 34. Yeah, that is one.
This one.
Yeah.
Absolutely. We run non-parametric tests here. You see the last column in this table, not the rank. So we calculate the rank of these measures, and we have multiple nested cross-validation loops plus bootstrapping on the holdout sample. And then we can show that we do significantly better, which is kind of intuitive from the average ranks that you see here. So yes, it's significantly better, but if you talk about the magnitude, and you do talk about the magnitude rightfully so, you may be able to establish significance, but not that you are substantially better, by no means.
And maybe this is another sampling bias. You only go for a micro loan as a consumer and ask a platform like an online credit platform of a bank if you are almost confident that you will get it. Yeah, so you have, in a sense, not many rejected. That's what I mean.
Oh yes, in microlending you do have, because they lend to people who normally don't get credit. So the kind of thin book clients, well, we saw that earlier. So by giving loans at random, they observed that the bad rate in the population was roughly 66%. And the acceptance rates of, well, this company is between 15 and 25% depending on which market they operate. They did business in Spain, Russia, and Poland, and acceptance rates were between 15 and 25%. So you do have many more rejects than accepts. That's inherent to the business.
Okay. We have one
and the
more
problem
question.
is that you can't really, oh, sorry.
We have one more question, so that's why, like, if you can probably discuss later. Valerio, you raised your hand.
Hi, Ala, thanks, and many thanks to the speaker for the great talk. Very interesting. I was wondering, I don't know if you're familiar with the, with the literature on, the econometric literature on propensity score matching. I was wondering, what are the relationship between the problem you deal with and the solution you propose, in relation to the literature? If
Wonderful.
you comment on that. Yeah, sorry.
Yeah, absolutely. So this is an important to do. In fact, we got this comment from a reviewer that we should also consider doubly robust estimator theory as a potential remedy. I now wonder, Valerio, whether you might have been that reviewer. Indeed. Honestly speaking, we kind of overlook that connection. We have, tons of tables of literature from various streams, but yes, the potential outcome framework, it comes into play here. So we will need to better understand this link and see whether this offers any alternatives. Yeah, so that's an to do.
If I can add something, the Bayesian perspective that you bring to that problem, that would actually be novel, if even to the, from the point of view of the econometric literature that has already looked at the problem. So this problem has been looked at, so to some extent, in some corners of the econometric literature, but the Bayesian perspective, if I understand it correctly, it's very fresh. Your approach, it can be very valuable. Also, to yeah.
I would love to talk to you afterwards as well, because this is absolutely, obviously correct. The Bayesian framework is built on self-learning. It's built on semi-supervised learning, which you could say is conceptually flawed for this problem. I think this is also what you are saying. Whereas in econometrics, we have potentially better solutions. Here we are dealing with a set of 2,000 features, which is why machine learning has its merits. But indeed, the very start from semi-supervised learning is kind of flawed, because semi-supervised learning does not really assume that labels are missing. It does assume that labels are missing at random, which is not the case here. We face labels that do not miss at random. And as you say, there are other solutions, starting with Heckman. On the other hand, well, often they don't scale very much. So currently we are involved with trying to use them, augment them. Yeah, I know, to make that possible. Thank you very much. You're basically providing these highly useful comments for future to-dos. Thank you very much for that.